So now we're going to be looking at standing sound waves, and these waves are a little more trickier. So this is resonance with sound and air waves. So in general, we're always going to be using the same formula, V equals lambda F. And similar to standing waves on a rope or mechanic, like on a physical medium like that, that's not sound or air, we're going to be talking about nodes and antinodes, but every scenario is going to be drawn a little bit differently. So in this case is, what is the fundamental frequency of a 0.672 meter long tube open at both ends on a day when the speed of sound is 344 meters per second? So I have an open tube here. Okay, and that's how I illustrate an open tube. And when I want to draw the wave, before what we talked about is I want to draw the fundamental frequency is the largest wave I can fit in here. And the requirement in an open area for resonance is that these are antinodes. That's what resonance sounds like when these are antinodes. And so the wave ends up looking, actually, in this case, the simplest wave the largest wave I can draw that will be an antinode at both ends is like this. Okay. Now a lot of times we do draw the other side. So I didn't do that in the standing wave problems, but we do draw the other side because we think of the wave as oscillating between these two modes. But however you like to see it. Okay, so what I need to know is the wavelength based on the length of the tube. And this here is half a wavelength. So the wavelength is equal to 2L, 2 times the length of the tube, which is 0.672. And that is 1.344 meters. Okay? And so the frequency from this equation is equal to V over lambda, where V is 344 meters per second, and lambda is 1.344. And so our fundamental frequency is 256 hertz. What is the frequency of sound in the second harmonic? Well, the next harmonic is going to be, it still needs to be an antinode up here, so I still got to start at the top up here. It's going to look like that. And then the opposite wave will look like this. Okay. And so for this one, we got to think about its wavelength here, right? The lambda for this one, well, the way if I look at kind of these eyes here, so maybe if I draw this other one, it might be useful to see. Each of these whole eyes that we would say these circles is half a wavelength. Okay, so I have half here, one here, and here. So there's like 2 of these whole things fit in here. So that means the wavelength is just equal to L. And so the frequency is V over lambda again, but it's 344. In this case, L is 0.672, and that will be 512 hertz. So just like in a standing wave on a string, which has nodes at both endpoints, the next harmonic is just double of the frequency. So you just do multiples of the fundamental frequency when you have an open tube. What is the length of a tube that has a fundamental frequency of 176 hertz, first overtone at 352 hertz if the speed of sound is 343 meters per second? Okay, so this is terminology again. Kind of like we draw, this is what the fundamental frequency looks like as one of these I things, if you will. So that means it's only half of a wavelength in here, so lambda is going to equal 2L. And my goal is to figure out what the length of this tube is. So velocity is equal to lambda F, and lambda is equal to 2L, and the frequency is given, and we have V. So I have V over 2F is equal to L by rearranging this. The velocity is 343. Divided by 2 times 176. The overtone doesn't really matter. This, of course, is double of that frequency. This doesn't really tell you anything. So that is sort of extraneous information because you should have already known that. 0.974 meters. A 512 hertz tuning fork is struck and placed next to a tube with a movable piston, creating a tube with variable length. So I have a tube here, and think of it as like the end here is adjustable. So I can move this up and down. And that changes the length of the pipe. The piston is slid down the pipe and resonance is reached when the piston is 150.5 centimeters from the open end. So we have a resonance. One resonance occurs at, how many meters is that? That's 1.155 meters. The next resonance is reached when the piston is 82.5 centimeters from the open end. So another one occurs at 0.825 meters. And these are adjacent harmonics. What is the speed of sound in the tube? And how far from the open will the piston of the next mode of resonance? Okay. So, yeah, and then the F is 512 hertz. So in this case, when we need to draw, this is a closed end and this is an open end. So we have to look at what the harmonics end up looking like. What does the wavelength look like? And in this case, it resonates, the fundamental will resonate at like this here. Like this. That's what the fundamental, because the closed end must be a node and the open ends must be antinodes. Okay. So this actually ends up being a quarter of a wavelength. Like this L is equal to 1/4 of an entire wavelength. So the wavelength is equal to 4L here. Okay. Now, what's happening is you got to think about, like, maybe think of it the other way. As I stretch it out, I can fit more of these things in here. Like the resonant frequency is going to change. I guess you don't know if the so let's do let's see. So I have 4L, I have L, I have the distances here. So I wonder if I can calculate what V is, for example. V is equal to lambda F. I'm just curious. I want to know what 4 times, say, 1.155 times 512 would be. Okay, it's probably not that high of a wavelength then. Yeah. So the tricky one about this one is you don't know which harmonic it is that this is happening at. But maybe I'll draw it a little bit differently. I'm going to draw it horizontally, and hopefully this will help a little bit. Let's just draw some wavelength that's happening in here. That looks like here, 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 and say here. This is like resonance. What they're really saying is, because the frequency is constant, I'm just changing the L, they're really saying that resonance, if my first resonance is this distance is 1.155 meters, that if I were to move this piston so that it closes is here, it resonates again, because you see this point is a node again. So this distance here is 0.825 meters. Okay, but it's the same wavelength, it's just different harmonics. I think is the way you want to think of it. And why would the wavelength be the same? Well, the wavelength is equal to the velocity over frequency, and this has to be a constant value. Because I know my frequency is 512 hertz, and the velocity is going to be constant. It's like the medium isn't changing. So I'm talking about a wave that has the same wavelength. Okay. And so we don't know which harmonic it is, but we do know that this distance must be half the wavelength from this picture, right? So this distance here has to be the 1.1155 minus 0.825, and I get 0.33. So 0.33 meters has to equal whatever the wavelength is. It has to equal half of that wavelength, or the wavelength is 0.66 meters. Okay. So now we need to know what the speed of. Now that I have the wavelength, I can find the velocity because I know it's lambda times F, and that is the wavelength being 0.66 and the frequency being 512 hertz. And that's 338 meters per second. Okay, so pretty close to 334. Okay, cool. So then the next one is, when is the next distance it's going to be? Well, from this picture, it's very obvious now. I just need to move an additional 0.33 meters. So I subtract 0.33 meters, and this distance here is 0.825 minus 0.33. It happens at an L of 0.495 meters from the open end, would be where the next resonance is going to be at. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.